Good morning, ladies and gentlemen. And let's have a discussion about the lengths of a curve in XY land. All of these lengths that we are going to talk about happen in XY land. In fact, 95% of the calculus that we study is in XY land. So what we're going to do is we're going to develop a formula to give us the length of a curve when y is a function of x. We know what these look like. These are the types of curves that we've been talking about our entire mathematics career. We're also going to then extend that formula to find the length of a curve when x is equal to a function of y. This is going to be somewhat new thought process, but we have looked at some functions of y, where x was a function of y. And then we're going to make the comparison to these two formulas to find length for the length of a parametric curve. And what's all this? The length of a parametric curve. Well, we've talked a lot about distance above crawls on a parametric curve from t equals a to t equals b, and we certainly have discussed this formula quite extensively. And that formula that gives the total distance above crawls on a parametric curve from t equals a to t equals b is this formula that we have used multiple times. The integral from a to b of the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and we're going to integrate that with respect to dt. With respect to t, we're going to integrate it with respect to t. This we've already known. So let's develop a formula that's going to give us this guy right here, the length of a curve when y is equal to a function of x. So let's go to the slide and look at here. I have the blue curve is a portion of a function where y is a function of x. And I'm just going to look at a tiny little, I'm going to look at a segment from this point to this point. I'm going to call that segment C there. That's segment C. And I'm going to look at this distance here, this horizontal distance. I'm going to call it dx, and this vertical distance dy, because you should know where we're going with this. We're going to make this c even smaller, and we're going to take the dx infinitely small and the dy infinitely small in a slide or so. And this length of this blue curve, this is what we want to approximate with this segment C, and we can see it's a fairly good approximation. If I zoomed out, maybe a better approximation. So let's just do some Pythagorean theorem work here. Our L is approximately c squared, and c squared is equal to, by the Pythagorean theorem, by Pythagoras' theorem, dx squared plus dy squared. And since c is a distance, a positive number, I can certainly see that c is the square root of dx squared plus dy squared. This is simple geometry, simple Pythagorean theorem. I have notes to go to the next screen, so I'm going to jump down here and go to the next screen down there. What I want to do, this is the formula, and I want to show you the formula before I give the proof of it. This is what I want to end up with right here. This is the actual formula. This formula is going to give me the length of the curve from A, and I have it marked off in those dashed purple lines. That's going to give me the length of the curve of y equals f of x from x equals a to x equals b. So you can see I'm going to integrate from a to b of the square root 1 plus dy dx squared with respect to x because I'm integrating, I'm having y as a function of x. So this is where I want to go on my next slide. And it's kind of not really difficult to get there, but it takes a bit of work, and we're going to slow down a little bit. We're going to go back. So this is where I want to end up. This is my claim here that this is true. So I'm going to go back to that slide, back to where I was, and I'm going to go back to this statement right there, where c is equal to the square root of dx squared plus dy squared. I have copied it again, and now look what I'm going to do. Now I'm going to look at this one thing, this guy here that looks like 1, and it is 1. All of these guys are 1. And I notice that dx divided by dx is 1. But another way to write dx divided by dx is dx divided by the square root of dx squared. The square root of dx squared is dx if dx is positive. So these two statements certainly are true. They both equal 1. So since they both equal 1, I can take this one thing and multiply it by the square root and not change its value. And that's exactly what I'm going to do here. I'm going to take that 1 and multiply it by the square root thingamajiggy. And look what I have. Now I have what I've done here is I've just taken this bottom and put it over that. But I can even put it in because it's a square root. And this is the little algebra steps here. If I have the square root of a plus b over the square root of a, I can certainly write that as the square root of a plus b over a. This is some algebra that we've done in the past, so it shouldn't be too difficult to see. And now, if you look at what's underneath the square root symbol there, I can simplify that as being dx squared over dx squared plus dy squared over dx squared. That's awful nice. This dx squared over dx squared certainly is 1, and I can certainly write dy squared divided by dx squared is dy dx squared. So that's my c. That's very nice because if I'm not mistaken, and I'm not, this is where I want it to go. So if I go to the next slide here. Oh, and look what I've done. Instead of doing this segment, what I'm going to do is I'm going to do all of these little segments where they are infinitely small. So I'm going to take that guy out of there. If I can get a hold of him, I think I can. And I'm going to erase this stuff here because what I'm doing is I'm doing for each little piece, I'm doing the same thing. And how do I add those up? I add up all of those segments and I go from A to B. I take dx infinitely small. Let me get something I can read there. Dx infinitely small and dy infinitely small. And that gives me the formula. And what formula does that give me? That gives me the formula and I have another picture here. Here's my little dx, my little dy. That gives me the formula for the length of a curve y equals f of x from x equals a to x equals b. Fairly straightforward. I just find the derivative of y with respect to x. I'm going to need this rascal in this formula. We can find those easy. I can find my upper limit, my lower limit. I take the integral from a to b of the square root of 1 plus dy dx squared. And of course, with dx, with respect to x, because I'm on the x-axis, I'm looking at y as a function of x. This, then, to show the length of a curve when x is a function of y is going to be very similar, if not the same. But what's difficult here is looking at, and we have not looked at enough of these, I will admit. We will look at more as in the next few weeks. But this is x as a function of y. It is a function if you rotate your eyes, it is going to be x as a function of y. For the input y, there's one and only one output, x. So this is x as a function of y. And really, to see how this is going to work, or to see how the limits of this formula work, we have to rotate our eyes. And I have a picture here, and we're going to zoom out just a little bit on that picture so we get both of them. So what this graph here, this is a graph of this guy that has been rotated. It has been rotated 90 degrees counterclockwise. And what you need to point out here, and we're not going to look at them like this, but I just wanted you to get an idea, of the limits, because that's where students get mixed up on. We have to realize that when we are looking at x as a function of y, these y's are the negative y's. These y's are the positive y's. I have the negative x's here, and I have the positive x's here. That happens because I'm rotating this xy 90 degrees. But if you look at it, we're really only going to look at it in normal xy land. Here, these are the x positives. These are the x negatives. These are the y positives, and these are the y negatives. So you may take a moment and dwell on what's happening here. So let's go back to our slide here, and let's see what we want to do. What we want to do is use the same process. We're going to use the same process to find this length. And again, I have a little triangle. I have this length C here. I do have this length C. It's going to approximate a portion of the curve, x equals f of y. I'm going to have a dy and a dx, and I know that c squared by the Pythagorean theorem is equal to dx squared plus dy squared. Same thing. No need to reiterate what I just talked about on the next slide. What's the only things changing around are the dx's and dys. Again, I'm multiplying it by 1, and you can slow this video down. You can pause the video to see what we're doing. It's the same exact discussion, where this is the point that's changing here. Instead of dx over the square root of dx squared, I'm going dy over the square root of dy squared, and the reason why I'm doing that is so that I get this dy out here. And so this is just an approximation for 1c, but as you know, and as we did before, what I want is a whole bunch of c's. I want to approximate all of these. How do I approximate? I want to approximate those with infinitely small dx's and infinitely small dy's. And how do I do that? How do I add them all up? I'm going to sum them with the integral symbol. And I put in a specific y and two specific y values, just so you know that you are conscious of the fact that the negative y's are down here and the positive y's are here, which you shouldn't have to think about, but it gets a little bit tricky when we write these definite intervals. So this is the formula that gives length of a curve, x equals f of y from, these are wrong. Thank you, Lee. You're welcome. From y equals -1 to y equals 3. And this is the formula right here. I have the integral from -1 to 3 of the square root of dx dy squared plus 1. The key here, if I have this x as a function of y, what I have to do is I have to take the derivative of x with respect to y, and that's where this is going to come from. So now I've gone over how I talked about. I've talked about finding the length of a curve when y is equal to f of x, from x equals a to x equals b. This is the formula. I have found the length of a curve when x is equal to f of y. This is the formula. Here I have from, again, This is from y equals a to y equals b. Getting ahead of myself a little bit. From y equals a to y equals b. And then we did review this formula that we've had in the past that gives it the distance or the length bug crawls on a parametric curve from t equals a to t equals b is the integral from a to b of the square root dx dt squared plus dy dt squared. And what you need to note, ladies and gentlemen, is that all three of these, all three look exactly the same. So should be some fairly easy problems assigned with this. This is not a difficult topic. Good day.